Okay, I was making a mention in the previous video that whenever exponential functions are there, stochastic independence can be possible. Whenever polynomials kind of things are there, stochastic independence may not be possible. Okay, in majority of the cases. Okay, let's see this problem. Again, you are being given joint probability distribution function or density function of f of x. You are asked to check whether x and y are independent. I have to go with marginal densities only, guys. Marginal densities only. Marginal densities of x and y I should be finding. Marginal density of x, we have seen in the previous video how to find it. Of course, since x and y are greater than or equal to 0, it's starting from 0 to infinity. Otherwise, it's from minus infinity to plus infinity. Okay. dy. When I'm finding for x, it is dy. Okay. Integral 0 to infinity 4xy e power minus x square plus y square dy. Okay. So whatever terms are there with respect to x, those are all constants like our 4. X is a constant, e power minus x square is also a constant. Only thing that I have to integrate is y into e power minus y square dy. And you know the substitution formula. You can go with substitution putting y square is equal to t or minus y square is equal to t. I will just do that later. Y squared is equal to t. So 2y dy would be dt. Okay, y dy would be dt by 2. That substitution I will be making. 4x e power minus x square is a constant. Of course, I should check the limits. When t is equal to 0, y is 0. When t is infinite, y is also infinite. So no change in limits of integration. Okay. Yeah. Y dy would be what? dt by 2. E power minus y square would be e power minus t. Okay. So e power minus t integration or differentiation exponential function is itself only because minus is there, it will come with a minus sign. Okay. X squared this is. And this would be what? E power minus t minus e power minus t by 2 from the limit 0 to infinite. For infinity, you know, 1 by e power infinity would go to 0, right? E power 0 would be 1. Okay, it's a minus sign. So what I'll be having finally is the answer would be 2 is there, 2 ones, 2 twos. So 2x e power minus x square for x greater than or equal to 0. That would be the marginal density of x. Okay. Similarly, marginal density of y, how I'll calculate, just see. F capital Y small y, this is equal to, of course, limits are from minus infinity to plus infinity, but x and y both are greater than 0. Okay. So F capital X Y, x comma y. This would be same answer, guys. Of course, here I have put dy, right? Here I'll be putting dx. For y it is dx, for x it is dy. 2y e power minus y square is what I will get. Now let us see. Let us see whether I am able to write what is that? F x y x comma y. F x y x comma y. Whether I am able to write like this or not, let us check. Okay. So what is there? E power 4xy e power minus x square plus y square is my LHS. What's my RHS here, guys? 2x into e power minus x square into 2y into e power minus y square. See what happens? 2 into 2 is 4. xy e power minus, if you take common, x square plus y square. LHS is equal to RHS. So I can say here that here f of x comma y, of course, in the suffix I can write this is independent, yes or no? I'm able to write like this stochastic. According to the stochastic independent definition, I'm able to write or not. Hence, I can say here that the given function is independent. That's what we were asked to check. Of course, you can as well find conditional density function. Okay, I shall show in case if randomly some conditional density function is there, how we'll do it for a continuous distribution. Okay. I'll do one more problem of stochastic independence if you want in the next video.